Welcome to the presentation of our paper, Binary Graph Neural Networks. My name is Mehdi and I'll be presenting today. This work has been accepted at CVPR 2021 and is a collaboration between researchers at Imperial College London and INRIA. Model compression techniques aim at reducing the memory and computational cost of machine learning models, often with the purpose of speeding up inference on low-power embedded devices, or to reduce energy consumption and increase throughput in the data center. Many approaches have been well studied in the past, such as low-rank approximations, pruning, or quantization, of which binarization is a special case, but they remain largely unexplored for geometric deep learning. In this work, we focus specifically on the binarization of graph neural networks. Compressing GNNs can be useful for many applications. We can cite embedded vision and 3D shape analysis, for example, for embedded point cloud processing, but also sensor networks and IoT, as well as data center applications like the mining of large-scale relational datasets that we have in social networks or bioinformatics. In order to understand the challenges of binarizing GNNs, we have to remember they are fundamentally different from CNNs. When Euclidean convolutions, meaning convolutions on grid-like structures like images, boil down to a single matrix product, graph convolutions are more general, and many of them fit the message passing paradigm that says that a graph element's features, like this node feature here, is updated as a function gamma, which is often nonlinear, of the previous feature map, as well as aggregated messages phi, of the features that depend on the features from the node itself, its neighbors, and the incident edges. And this shows that we need to make more design decisions when we want to binarize general graph convolutions. As a case study, we can look at the dynamic graph CNN model. So contrary to concurrent work on the binarization of GNN that focus on models like GCN and graph attention that only involve dot product operations on node features, DGCNN is based on the edge-conv operator that is the max aggregation of edge messages that depend on some edge feature defined as the difference between the node features at the node and at its neighbors. The model is also applicable to both graphs and point clouds, and in the paper, they build the graph dynamically by k-NAND search in feature space for point clouds. And this is an example of a model for which binarization has non-trivial implications if we binarize the node features as well, because we would have to deal with the edge features. So, as a first approach, we propose a direct binarization strategy that is derived from XNorNet++. XNorNet++ approximates tensor dot products by their binary dot products and a real number rescaling. And this keeps the output real valued. So this is a drop-in replacement for edge-conv, but it doesn't speed up other operations like k-NAND. And this is why binary graph features are desirable. k-NAND search is a bottleneck on real valued vectors, but is very fast in Hamming space because the Hamming distance is extremely fast to compute. The issue, as we said before, is that we have to redefine the edge features, and the solution we found is to replace the subtraction by the corresponding operation for binary vectors, in this case the exclusive OR. We also have to permute the order of the operations such that quantization comes last, and this raises the question of where do we put the Batch normalization, because the position changes the distribution of features pre-quantization, which has been shown to potentially matter in some recent work on binarizing point cloud networks. So we tested two different positions. We can first aggregate the messages, then normalize and quantize, or we can first normalize the messages, then aggregate, then quantize. In all cases, we employ a three-stage progressive quantization strategy inspired by the state-of-the-art on image CNNs. We also use recent advances in distillation for GNNs with the LSP module, and a relaxation of the Hamming distance to enable quantization-aware training. Our experiments on point cloud classification show that binEdgeConv, our model that keeps the output real valued, comes within 2% of the baseline when using binary weights and activations. XorEdgeConv is the model that produces binary node features and comes within 10% of the baseline when also using binary weights. However, if we relax this requirement and use floating point weights but keep the node features and the activations binary, we come back to being within 1.5% accuracy of the baseline. And this shows that we can strike some balance between speed and accuracy, or remain competitive in accuracy but speed up both bottlenecks, being the quantization of the convolution and the k-NAND search. So we also performed some experiments on large-scale inductive learning. One early approach, fundamental approach to scaling GNNs is sampling. of fixed-size neighborhoods around nodes to control the computational cost of the process. One such example, very prominent, is GraphSage, which is described by this equation, and that we binarized as for RubyNetConf. We evaluate the binary GraphSage model on two very challenging benchmarks from OGB, the OpenGraph benchmark. OGB provides standardized evaluators that ensure a fair comparison, and also contrary to other benchmarks like Cora or Reddit, the graphs have high average node degree and small graph diameter, which has been shown to potentially exacerbate some of the limitations of GNNs. In all cases, we achieve near floating point performance, and on OGB proteins, our binary GraphSage outperforms a floating point GCN. So this shows that we can successfully combine binarization and sampling for scaling GNNs. So due to time constraints, I cannot go in depth over these results, but in the paper, we carried out a detailed ablation study of the different parts involved in our method. For example, the choice of activation function, the use or not of recentering of the activations prior to quantizing, defining new LSP kernels on binary features with Hamming distance, the impact of the three-stage progressive binarization strategy, as well as training on binary node features using KNN performed with the Hamming distance, the relaxation of the Hamming distance over the L2 distance. All results are summarized in Table 1 of the paper. In particular, we were able to confirm the effectiveness of the three-stage distillation approach, as we can see here, and the choice of p-ReLU activations compared to not using any activations or using ReLU activations. However, we did not observe an advantage in recentering the activations prior to max aggregation and quantization, either at the edge level or at the global embedding stage. Finally, we carried out some real-world benchmarks on the Raspberry Pi 4B using the LARC runtime. And we tried 4 different optimization levels, starting from the baseline floating point GCNN, all the way to the model that uses the operator that produces binary node features and uses binary weights and binary activations, with an optimized, or rather a simulation of an optimized Hamming distance implementation, as we will explain why. So in this runtime, concatenation and top K are currently not accelerated by binarization. We denote them as incompressible operations because they are often performed in the GCNN. We also could not, at the time of writing, integrate a vectorized implementation of the Hamming distance. So instead, we took a conservative estimate of the speedup that ARM Neon instructions would bring to a non-optimized implementation of the Hamming distance. Keeping these implementation challenges in mind, we observed a 2x empirical runtime speedup, as well as significant reductions in memory usage and model file size. And all the different variants are explained in this table over here. Thank you for listening to the presentation, and I hope to see you soon for questions.